Bismillah and Assalamualaikum. My name is Muhammad Zufakar bin Zamri. Today I'll in charge to introduce about the introduction, to present about the introduction. Okay, first and foremost, we go to the alias, names and number matrix. First, our leader Ahmad Adham bin Abdul Hadi, number matrix AA191890. The second, the co-leader is Muhammad Haiman bin Yassin, AA191605. Third one is Muhammad Fakrul Amin bin Abdul Rahim, AA1910 excuse me AA191710. The next is Muhammad Ishak Hakimi bin Radwan, AA191157. And the last one is me, Muhammad Fakar bin Zamri, AA190113. Okay, first let's go to the table of content. They have three big topic that we will discuss in the project. The first one is introduction, the part that are in charge. The second one is the result and the discussion, the conclusion, and the last one is the reference. There are four divided topic that we will discuss today. Introduction. The PID controller is widely employed because it is unstable by any other engineer. One interpretation of the PID controller is that all engineers understand constantly differentiation and integration, so they can implement the control system even without a deep understanding in the control theory. Further, even though the computer is simple, it is quite sophisticated in that it captures the history of system through integration and anticipate the future behavior of the system through differentiation. Okay, done with the very simplest introduction. Okay, the next one is the implement of the PID. Position from the PID of the PID controller is involves direct discretization of the continuous time controller. There are only two types of PID control using the velocity form for the implementation. One is proportional PI control and the other is PID controller. In the velocity form, the PI controller or PID controller is discrete without separation of individual terms, and the solution focus on the derivatives of the control variable from which come the term velocity. The implementation of PID controller requires the consideration of an anti-one-up mechanism in the presence of constraint on the control signal. There are many approaches available for implementing PID controller with an anti-one-up mechanism. Okay, we go to the next one is the application of the PID controller in industry and domestic use. The first is MPPT charge controller. The VI characteristic of the photovoltaic cell mainly depend on the range of the temperature as well as the irradiance. Based on the weather conditions, the current and the operating voltage will be changed constantly, so it's extremely significant to track the highest power point of the efficient photovoltaic system. PID controller is used to find the MPPT by giving fixed voltage and current points to the PID controller. Once the weather condition is changed, then the tracker maintain to the current and voltage tables. I hope that you follow me with my explanation. Okay, the next one is the converter of the power electronic. PID controller is mostly used in the converter whenever a converter is added to a system and based on the change with the with the load. Then the converter output will be changed. For instance, and the inverter is added with load. The huge big current is supplied once loads are increased. Thus, the parameter of the voltage well of the current is not stable, but it will alter based on the requirement. Okay, the next one is the temperature control. the temperature control of furnace. Okay, furnace are used to include heating as well as hold a huge amount of raw material at a huge temperature. It is usual for the material to occupy to include huge mass. Consequently, it may have high quantity inertia of the temperature, and the material doesn't modify rapidly even when is applied. This feature results in the moderately stable PV signal and permits the operative period to efficiently correct correct for file without extreme changes to either the FCE or the CO. Okay, the next one we should go to the example of a control other than KID controller. Okay, I would like to choose the proportional and integral controller, PI control. A combination of the proportional and integral control, the output, also called by actuating signal, is equal by summation of proportional and integral of the error signal. A proportional and integral control output is directly proportional to the summation of proportional of error and integration of the error signal. Okay, Ki and Kp proportional constant and integral constant respectively based on the formula that given. There. Oh, there. Okay. Output for power equals to the sum of the proportion and integration coefficient. The higher the proportion coefficient, the less the output power at the same control error. The higher the integration coefficient, the lower the accumulated integration coefficient. PI control provide a zero control error and insensitive to interference of the measurement channel. The PI control disadvantage is low reaction to disturbance. To adjust the PI control, you should first set the integration time to equal to 0 and the maximum proportion time. Then by increasing the coefficient of proportionality, achieve predictive oscillation in the system to the close to the optimum value of the coefficient of proportional is twice higher than and at which any hesitation and close to the optimum value of the integration time of constant is 20% less than the oscillation period. I think that's all from me. Thank you, and let's hear about the others presenter to present their parts that they are in charge. So thank you for lending me your ears.
Dirham bin Abdul Hadi. Nama matrik is AA191890. Okay, now my turn. I will explain the transfer function one. Okay, this the transfer function one we use the Simulink academic. Okay, this is transfer one Simulink. Okay, now in the Simulink you have the step. The step time is 0, initial value 0, final value is 1, sample time is 0. Okay, next we look at the sum like this, positive negative, and then the transfer function is 9 uh, 9 per s square. Okay, we look at the parameter. Numerator coefficient is 9. At the denominator coefficient is 1, 0, 0. This is a auto absolute tolerance. Okay, we apply and okay. Now we go to the run the program. We run and then we click the scope. Okay, click the scope and then okay, this is the scope of this transfer function. The graph is a equal shape like that. Okay, the transfer function scope we already done. Okay, next we go to the MATLAB. Okay. Okay, now we at the MATLAB to find the locus, to find the transfer function, feedback, locus, step response, step info. Okay, the first of all, we want start. We type t equal tf transfer function 9 1 0 0. Okay, okay, this transfer function. Next, the feedback, we use a f equal feedback t. We use a t because the transfer function t 1. Alright. Okay, this feedback. Next, we go to our locus. Type the our locus feedback to find our locus f. Okay, now this is a locus. Okay, next we go to the step response, step f. Okay, this step response. The graph of step response, and then we look at step info. Step info f. This is transfer function 1. Okay, okay, this is answer of a step info. Rise time is 0.3473, settling time NAN, settling mean 1.0851 E, diff 15, settling max 2.0000, overshoot 100.0000, undershoot is 0, peak is 2.0000, peak time is 1.0472. Okay, thank you. That's all for me. The transfer function 1. Next, we go to transfer function 2. Okay.
My name is Muhammad Irshad Hakim Bebe Muhammad Ridwan. My metric number is AA191157. I'm gonna explain about transfer function 2, which is 9 over 2 s square plus 0.6s. In the numerator column, we fill we put 9. In the denominator column, we put 1, 0.6 and 0. After that, we apply and okay. To find out the step response, we run the block diagram. After that, we click to the scope. This is the step response with the ID controller for transfer function 2. The graph is marginally stable. After that, we find out the step response without PID controller. T equal to TF 9 1 0.6 0 feedback T 1 step. Um, we put grid on, and then we look back at the step response. This is the step response for the transfer function 2 without PID controller. After that, we need to find out the overshoot, setting time, and steady state. To find out the overshoot, we pick at the peak response, and we can see the overshoot is 72.9. To find out the setting time, we pick the setting time. Setting time is 12.8 for this transfer function, and steady state for this transfer function is 1. But we can easily find out the info without uh, picking like that. We just put the common step info F, and then we can see the setting time is 12.7910. The overshoot is 72.9156. Okay, for activity 6, um, we must try the different value of KP and observe the overshoot, setting time, and steady state based on the graph. Okay, first num equal to 9, denom equal to 1, 0.6, and 0. GP equal to TF, num denom, H equal to 1, M equal to feedback. Then step M, and we turn on the grid. After that, we run the command to find out the step response. Okay, this is the step response for transfer function 2. The the overshoot is 72.9. The setting time is 12.8. The final value, the steady state is 1. After that, we change the KP value. We put the KP value to 0.5, KI to 0, and KD to 0. GC equal to PID KP, comma KI, comma KD. After that, MC equal to feedback GC GPH. Then step MC read on. We run the command back. Okay, this is the step response for transfer function 2 with the KP value is 0.5. Okay, as you can see, the overshoot decreased to 63.8. The setting time is 12.3 second, and the steady state still same 1. Let we change the KP value again to 2 and to 1. We run the back. Turn on the peak response, setting time, and steady state. Find out the overshoot, setting time, and final value. For the transfer function with Kp equal to 1, overshoot is 72.9, setting time is 12.8 seconds, and steady state is 1. Next, we change the value to 2, and we run the command back. This is the step response with Kp equal to 2. We turn on the ping response, setting time, and steady state. Okay, for the Kp value equal to 2, the overshoot become to 80%, and the setting time is 12.7 seconds, and the steady state is 1. So the best value for the Kp is 2 because the overshoot is more higher than Kp equal to 1 and Kp equal to 0.5, and then the setting time for the Kp equal to 2 is more longer than Kp equal to 1 and Kp equal to 0.5.
Satu. My name is Mama Aiman bin Mama Yasin, and my matric number is AA191605. Now for the transfer function number 3 is 1 over 0.8 s power of 2 plus 2s plus 200. For the transfer function must be on a plan. So to find the graph, we must highlight this graph and select the data inspector. So and then we run the circuit, and then we will get the graph, and this graph is underdamped. Next, to find the original closed loop control system, the first one is overshot. We will get 78%, and then for the settling time we get 3.02 second, and the final value is 0.00498. Next, the PID control closed loop control system. For the transfer function number 3, we use Kp equal to 40, KD equal to 20 and KI 0.1, 0.2 and 0.3. The overall for KI value 0.1, 0.2, 0.3 to overshot, we don't get any value, but the settling time for the KI 0.1, we get 0.009. KI equal to 0.2, settling time we get 0.004. And KI equal to 0.3, we get 0.003. For the state error, all KI equal to 0.1, 0.2 and 0.3, we've got 1. I think that's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Fakrul Amin bin Abdul Rahim. My number matric is AA191710. I'm from section 6. So today I will present about the control system project, and my part is for the transfer function 4. So here we can see the block diagram of transfer function 4. Okay, and then we look at the Simulink model and we write the transfer function here in the box, and the next thing we must run the simulation. Okay, after we run, we click at the scope to see the step response. So the result is like this. This is show that the graph is unstable. Tidak stabil lah, unstable. You can see here. Okay. Next, we move to the characteristic of original, closed, P control, PI control and PID control. Okay, next we look at the command. For the characteristic of original closed loop control system, just run. And we can see this infinity. This is infinity. Then we record on the in the table of transfer function 4, infinity. Okay, next we move to the characteristic of the P control. So we put the value of transfer function 4. Here is 20, 40 and 60 for the P control. So this is the value. Then we change to the 40. Then we run. We got this. And 60 we run. We got this. And then we move to the, after we done for the P control, we move to the PD control, and for the PD control we put the nilai, we put the KP all 40 and KD 10, 20 and 30. This KP we put all 40, let's we change it here 10, then we run, and then we get this 20, and then we run, then we get this 30, we run, and then we get the result like state response is here. Here we can see that peak response, there's no peak response, we get the setting time, and then we go to the steady state error like this 0.983. Okay, and then we move to the and then we move to the characteristic of PID control closed loop control system. We get to see to the transfer function 4. So we use all KP40 and KD all 20. We just use 700 and 390. We use KD all 20, and then we have to change here 700. And go to run. So we got to see the static response, setting time, and steady state. So we can see here system is value 1, and we change to 800. Let's run. And we get the same here, we get to see the response, and then setting time, we get to see the steady state. And the last is 900 for the PID controller. So we run, we get this MC, and we get this speed response here, that setting time and steady state. So this is average is below 5 and below 2, and this below 2. Below 10, below 5 and below 2. Okay, that's all from me. Thank you. I think that's all from me. Thank you.
Okay, now I will present the conclusion. Conclude the effect of PID coefficient for each transfer function. Okay, for the transfer function 1, P controller is increase the volume overcome, and there is no change in finishing time errors and fixed condition. Second, I controller is reduce volume too much time and effort eliminate fixed condition errors. Third, D controller is reduce volume too much time and effort eliminate fixed condition errors. Okay, next transfer function 2. P controller is increase the volume too much time and effort eliminate fixed condition errors. Second, eye controller is remove overshoot and fixed condition errors, also reduce finish time. Third, decontroller is eliminate overshoot and fixed condition errors, also reduce finish time. Okay, next, transfer function 3. Controller is increase overshoot and reduce settlement time. Is small change. Small change also reduce fixed condition errors. Eye controller is removes overshoot and fixed condition errors. Also reduce finish time. Third, controller is reduce overshoot and finish time. Also no change to stable state error. Okay, transfer function 4. Controller is not change in overshoot resolve time and fixed state errors value. Eye controller is remove overshoot and fixed condition errors, also reduce finish time. Controller is reduce overshoot, resolve time and fixed state error. Okay, next, conclude which controller performs best for each transfer function. The transfer function 1 indicates that the PID controller is a sufficient controller to reduce overshoot and establish steady state errors. The addition of proportional controller and derivations derivative only makes the PID controller necessary to make the system stable. The transfer function 2. The output system is sine wave, like that is state response. So the best controller that perform is this system is PD controller. When we use PD controller, state response closed loop control system at KD10 is logarithmic graph and KD20 and 30 is square root graph. Okay. Transfer function 3. For the transfer function 3, show that the PID controller is the controller that is enough to be able to reduce the overshoot and the steady state error. So the best controller that work in this system is the PID controller. When we use the PD controller, the output of the system will get 0 steady state error, 0 advantage. Okay. Lastly, transfer function 4. The transfer function 4 indicates that the PID controller is the most suitable controller to be able to reduce overshoot and steady state errors under need, and the system is very stable. Values are Kp is 40, Kd is 10 and Ki 0. The pre-PID controller, which is P and PD, is only able to reduce solution time and reduce overshoot but cannot make the system stable. Okay, that's all from we. Thank you. Assalamualaikum warahmatullahi wabarakatuh.